First of all, thank you very much for inviting me to talk about exoplanets and CHEOPS. And even though it's online, I see there's a lot of people, so this is really great. Of course, it would have been much nicer to do this in person in Tenerife. But thanks everybody for joining. So I'm gonna change scales a little bit now, and we're going from black holes and things that are generally quite far away and large to things that we can actually, at least to some extent, imagine more realistically. So in the solar system, we have a number of planets that you can see here. The nice thing about these is that we can really go there, we can really take pictures, we can even send probes and study the atmospheres in detail. Now, of course, we all know that the solar system isn't the only solar system out there, but there are many exoplanets. And so I'm gonna talk a little bit about what we can learn about exoplanets. So for exoplanets, the best thing we can do about imaging is about what you can see here. There are a handful of planetary systems that have been imaged directly. These are very complicated observations, and at the current state of the technical possibilities, we're sensitive only to systems that have very massive planets, that have very luminous planets, therefore very young planets, and planets, of course, that are very far away from their host stars. So these directly imaged planets are not necessarily the best objects to compare directly to our solar system, but it's still quite impressive to see that we can actually already get there. So the planets that I'll be talking about more in this talk are planets that we can only measure indirectly, namely through planetary transits, shown on the left, where we have the planet passing in front of the star, and we measure variations in the system brightness that contains flux from both the planet and the star, and planets that we measure in radial velocity variations, where we measure the reflex motion of the star created by the planetary orbit. And that reveals to us the planetary mass. Now, the exoplanet field really, since the detection of the first exoplanet, has gone through a large boom since 1995. Just to give you a little feeling about how the parameter space has been filling up with planets going to lower and lower masses. I've put this simulation here. You can see on the left also the evolution of the different spectrographs that's been going on, going from spectrographs in the 90s that had a precision of at most about 10 meters per second to routinely reaching precisions of 1 meter per second with instrumentation such as, of course, HARPS North for the Spanish community, Carmenes, and also PFS for the American community. And then finally, we're now going to another order of magnitude with instrumentation such as Espresso that actually works at the VLT and that is capable of combining the light of all 4 UTs together to maximize really the precision of the observation. For transits, the evolution has been even more striking, I would say. Let's look a little bit at the simulation. You see how the parameter space is really filling up massively. Here again, we went from the detection of some hot Jupiters, so close-in gas giants, very massive planets from the ground, to the first rocky planets, the planet that was discovered by Corot, and then, of course, the Kepler satellite that stared at the region in the sky for several years, that really produced a large number of small planets. And the main result really has been that small planets, as you can see on the left, are very common. And now finally, these days, there's the TESS mission that is observing more or less the whole sky with small regions that are accepted. And it's really looking to find transiting planets orbiting bright stars. It's not quite as sensitive as Kepler. It can't really go to signatures that are as small, but it's nice because the Kepler targets were quite faint globally, but the TESS targets, they're pretty bright stars. And that, of course, is very nice because that allows us to follow up these targets in more detail. Now I'd just like to use this mass period diagram that tells us roughly about the distribution of extrasolar planets in their parameter space to illustrate three main findings, or three main questions that we're asking ourselves in the exoplanet community. So just to summarize, we have cool Jupiters, we have hot Jupiters, so gas giants at very close orbital periods. We're having an ever-growing population of planets that are in between the size of about half a Jupiter mass and about 2 Earth mass, Earth radii. We call these super Earths, so mini Neptunes, depending on a little bit whether we're believing them to be rocky or having a gaseous envelope. I'll come back to that. And then finally, more and more rocky planets are being discovered as well. So the first question is planetary migration, right? So we have all these gas giants at short orbital periods, but it is unreasonable to assume that these planets have actually formed there. It is more likely that these planets were formed further out at several AU and then moved in during the evolution of the planetary system, maybe even during its very early phases. So there's two mechanisms that we are, that both appear to be plausible to be responsible at least for some of the observed system each, either dynamical interactions, simply multi-body dynamical interactions that make a planet reach a very elliptic orbit that then gets circularized and reaches small circular orbital distances. And then disk migration, so while the planets are embedded in a protoplanetary disk, they move towards the star through to due to the interaction with that gas and dust disk that they're embedded in. And so, of course, one thing that a lot of people are really curious about these days is whether or not the composition of these hot Jupiters, because that's something we can actually start to measure, will tell us something about the way the planet ended up where it is, about its history. The second characteristic of this distribution, I've swapped here the planet mass against the planet radius, is that there in this triangle here, we call it the evaporation desert, there are no planets, or very, very few planets. So why is that? Why are there no hot subsaturans? Now, the most well-established belief here is that this is due to atmospheric erosion, because these planets that would have smaller masses and are located so close to the star, while being irradiated so strongly by their host star, they're simply not able to keep their gaseous envelope. So there have been already observations of Neptunes and mini Neptunes that have been shown to lose strongly their hydrogen envelope. And it's simply believed that these hydrogen envelopes simply get lost over relatively short periods of time. And another point of study is then those planets that don't quite manage to lose all their hydrogen. How do these hot Jupiters, how do these react to that strong irradiation from their host? So there have been some observations already about that trace the wind structures going on these planets. It appears that for planets that are not the most highly irradiated, but planets of, say, a temperature of about 1000 Kelvin, we find very pronounced jets that orbit the planet and circulate the energy from day to night. But for planets that are hotter, we call them ultra-hot Jupiters, hotter than about 2500 Kelvin, this seems to break down, and these planets really get cooked from the star and heat up massively on their day sides. And the third point that I'd like to stress is this little depression here that I've indicated with the dashed line. This is statistically significant. There's been a number of papers about this. We call it the radius valley. So there are comparatively few planets that have a radius of about 1.8 Earth radii. That's about the location of this radius valley. Now, why is that? We believe that this is kind of the separating size below which the size corresponds to a planet that has a predominantly rocky composition, and above that size, we're looking at planets that have manage to accrete and to keep a substantial amount of hydrogen and helium in their atmospheres. The reason why that's the case, so again, there are several possibilities. The most commonly explored possibility is that this is due to evaporation during the formation of the planet, due to the host star's XUV flux. So that simply, it's also because we see a slight dependence of this radius valley on the planetary period. It simply means that planets that are exposed to more XUV flux during their formation have a harder time in accreting gaseous envelopes. And I'm going now to the CHEOPS satellite, which I'm going to describe to you a little bit, and I'm going to try and describe to you how with CHEOPS we're addressing these three different questions that I've just highlighted. So first of all, what is CHEOPS? CHEOPS is the first ESA S-class mission, and it's dedicated to study known exoplanets. You can see a picture of CHEOPS down here on the left. That's the telescope itself, while it was at the University of Bern. And it's a pretty small thing, actually. So the size of the mirror is just about 30 centimeters. But don't be mistaken, this is a space telescope, and it's really been optimized to perform ultra-high precision photometry. So what do we mean when we say ultra-high precision photometry? The goals that were specified at the conception of CHEOPS, right? They were to reach 20 parts per million over 6 hours for bright stars, which in fact is what is needed to detect transits of Earth-sized planets around solar-type stars. And then going to a little bit fainter stars, of course, the precision is not quite as good, but here the goal was really to measure precise radii for super-Earths, for planets that are just at this transition between rocky and gaseous compositions. And so the goal really here is to target planets that fall into this group, these super-Earths and mini-Neptunes down here. However, we already know these planets exist, but since they were observed by Kepler, these are mostly orbiting faint stars. We also have a number of these planets detected in radial velocities, but most of these radial velocity planets don't transit. So CHEOPS, the goal really for CHEOPS here was to measure precise radii for planets orbiting bright stars that have masses measured with radial velocities. So there are programs within the CHEOPS GTO to either go to planets that we know are transiting, but we know their masses from radial velocities, but we don't have precise radii. We go back with CHEOPS and derive and measure a very precise radius. And then there's another program that is dedicated to observing radial velocity planets. So a planet, we know it's there from radial velocity. We don't know yet if it transits, and search for the transit of the planet. And from these observations, of course, the goal is to determine the bulk composition of these planets, whether we're looking at planets that have a large hydrogen helium envelope and a small core, or planets that have a more substantial fraction of volatiles, of water, of CO2, and so on in their atmospheres, or even planets that have basically just a rocky core and a very thin atmosphere. And then another science goal of CHEOPS really is to understand a bit more about those ultra short period planets. So the rocky planets that are very, very close to their host star. And for example, the pretty famous super-Earth, 55 Cancri E, it's orbiting its star at a period of less than a day. And interestingly, from previous observations, it looks like the planet itself is variable. So something is changing with time. What you can see here is the occultation, the passage of the planet behind the star. And one season it appears to be really deep, and the next season appears to be much shallower. So something is going on the planet, right? And then the phase curve is something that I looked into with one of my postdocs recently. Also the phase variation, so the amount of light emitted from the system along the planetary orbit appears to be variable with time. So one way of explaining this, and this is a theory, is that the atmosphere of this planet is actually variable in time, and that from time to time the planet appears to be losing some material that then accumulates in the planetary orbit and creates these variable signatures. And then finally, the hot Jupiters. I've mentioned these planets already a lot, these highly irradiated gas giants. Here, what's pretty cool is that since they have their short orbital periods, we can observe throughout the whole orbit of the planet and measure how the flux varies with time. And this then tells us about the emission from the planet, not only from its day side, but also resolved longitudinally. And it tells us about the flux distribution on the planet, emanating from the planet. And so these observations then tell us something about the emission from the planet. But for slightly cooler planets, where we have reason to assume that there are atmospheric aerosols, so clouds or hazes present, tells us also something about the reflection of the planet. And so here, the goal of CHEOPS is to understand better how these gas giants process the heat that's impacting on them. On which planets do we actually have this formation of reflective clouds? And if so, how do these clouds distribute across the atmosphere? How are they transported around the planet? So I'll skip over this a little quickly. This is just saying we're a small mission, but it's not been easy. We've only had 5 years from adoption to launch, but everything went as expected, and the instrument was assembled and tested and eventually launched to space. So I do let you look at this launch video. It was a very impressive launch, just at 6 a.m. in the morning, to reach a day-night terminator orbit that goes over the poles. Yeah, so where is CHEOPS now? So since the launch, CHEOPS has been switched on, of course. This here is just a dark frame, but it's probably one of the most emotionally charged dark frames that I've ever seen, because it told us that everything was working fine. And then on the 29th of January, we opened the cover of CHEOPS, the one moving part that the telescope possesses. Everything worked fine, and we're observing on sky. And soon after, we of course started to test the telescope. And one of the first and most important tests was to do a nearly 2-day consecutive sequence on a bright star. This here is simply a stable 9th magnitude star. And you see indicated here the 6 hours over which we expected to reach a precision of 20 parts per million. We reached 11.2 parts per million. So we've not only reached the instrument goal, but we've actually exceeded it by a large margin. And so I'd like to conclude by showing you the first scientific observation of CHEOPS. Here, this is the transit of a hot Jupiter that is, however, quite different, quite special, let's say, because it's not transiting a main sequence star, but it's transiting a star that is already slightly evolved, Kelt 11. And so the transit itself is relatively shallow. So this is what it is. It's just over 2 millimag, the transit. And you can nicely see that we precisely measure the transit. It's detected at an extremely high significance. And putting it into relation or measurement has the precision of a little less than 2,000 kilometers in relative size of the planet. Now, I'd just like to conclude with a little note here. You might notice this correlated noise that is still present in the light curve that looks a bit, that might be instrumental or something. So it's not actually, what we're seeing here is the variation of the stellar surface. So it's actually the star due to granulation that is varying just slightly. And that's what we see in our light curves. So this will be another application of CHEOPS. So if this all talks to you and you'd like to use CHEOPS, there is a guest observers program. The next call will be open in fall. So don't hesitate to submit the proposal. It doesn't need to be exoplanet science. It just needs to use the capabilities of CHEOPS. And with that, and my own alarm going off, I'm going to stop. Thank you very much.
Okay, thank you very much. We have already a couple of questions. I don't know if you can read them or I read them for you. Yeah, the first question is, has the eccentricity distribution of the transiting planet been measured? And how do we know if there are differences between the rocky hot Neptune and Jupiter planets in their eccentricity distribution?
In their eccentricity distribution. So the eccentricity distribution is not the most straightforward thing to measure because you generally need radial velocity observations to get good constraints on that. We do know that the eccentricity distribution of exoplanets, but mainly for planets that are more massive, is quite different from the solar system. So we have gas giants or large planets that have eccentricities of up to 0.9. So there are many more eccentric planets. For the smaller planets, however, we often see multiple systems, so a system with up to 5-7 planets, but then they have very circular orbits because if they were eccentric, they would become unstable.
Thank you. So the next question asks, is there any hint of why the green dots Earth are kind of separated from the other measurements, red dots? Is this due to limitation in technology or methodology? Or?
It's our limitation in technology at the moment. So this is actually a very good point to make. We are currently not yet able to detect a solar system analog. We're just about able to detect another Jupiter, an exo-Jupiter, but even an exo-Earth, we're just not quite there yet.
Okay, if there are any other question or anybody's furiously typing, I'll give you another few seconds. Otherwise, let's all thank Monika. Thanks a lot for this very interesting presentations.